Hello guys, in today's video we are going to discuss the invertibility of elementary matrices. So you might wonder what an elementary matrix is. So an elementary matrix is such a matrix which corresponds to a row operation. So when you do row operations to convert your matrix to say the echelon form or any other form, you perform certain row operations such as adding a row to another row, scaling a row, or interchanging rows. All of these operations can be represented as multiplying the matrix with an elementary matrix. So today we are going to prove that these elementary matrices are invertible, which in turn would also support the claim that these row operations are invertible. So today we are going to prove this for the row operation where we add one row to another. So let's say we have row I, then we change it to row I plus C times rho j, where C is some scalar and rho j is some other row. So I is not equal to j. If I had been equal to j, it would have been equivalent to adding the same row to itself, which would not have been adding two different rows, rather it would have corresponded to scaling the same row. So let's begin with the proof. Um, okay, let me make some space here first. Yeah. So first of all, a matrix E. Let's say we have a matrix E which we want to check if it is invertible or not. So our elementary matrix is E. We can say it is invertible if there exists F. So this is a symbol for there exists F such that E times F is equal to F times E is equal to the identity matrix I. So this is what we are basically going to prove. So again, the notation which I'm going to use in this proof is this: row ij is the matrix, the n cross n matrix, which has all zero elements except for one, which is the ijth element, except for the ijth element, that is the element in the ith row and the jth column. So again, let me get some more space here. Okay, so then we can write E, which is our elementary matrix, as the identity matrix plus C times some row ij, right? Similarly, we can write F, which is the matrix which is the inverse of this, as I minus C times row ij. This minus because first of all you were adding a row, the jth row to the ith row, and you had multiplied the jth row C times with a factor C. So when you do this operation, it would invert it because you would be subtracting the jth row multiplied minus C times. So in effect, it would have cancelled the initial change. So EF should correspond to I. This is the intuition. Now we're going to prove it. So if you multiply E and F, what you would get is I into I square, which is again I. You would get a term of I minus 0 ij and I plus 0 ij, which would cancel to give a 0, and you would get this minus c square rho ij square, right? Similarly, if you had computed fe, it would have also come out to be the same. You can check that yourself. So now what we have proved is the first part, which was ef is equal to Fe. However, this is not the complete proof because we need to prove that EF is equal to Fe is equal to the identity matrix. Otherwise, there can be a lot of matrices who are designed such that when multiplied in any order, they give the same product. So let's continue our proof here. So you might see here that C can be any scalar, right? So to get only the identity matrix on the RHS, we need to prove that row ij square is 0. Only then will our claim that EF is and FERI will be proved, because this row ij square, if proven to be 0, will eliminate this c square row ij square term from both sides. So we need to prove row ij square equals to 0, but we also had this condition when I is not equal to j, because we are not talking about the scaling operation. If I is equal to j, it would correspond to the scaling operation. Okay, again some more space is needed. Yeah, so let's rewrite this. If we take row ij square and let's take the element in the kth row and the lth column, then it can be rewritten as row ij into row ij, so multiplying those two, and the element then in the kth row and lth column, right? Which in terms of the sigma notation would be sigma m is equal to 1 to n row ij km into row ij ml. So how did I get this? Because when we multiply two matrices and look for a particular entry, the kth in the kth row and the lth column, for the first matrix we take the kth row, right? And then for instance we have two matrices and we are multiplying them. Then we take a row from here and a column from here and multiply those, right? So we took the kth row from here and the lth column from here, and that would correspond to the k lth entry in the product of those two matrices. So we have reached this step. Now we're going to bifurcate, or like divide our proof into two steps, into two different sections. So for the first section, let us take the cases if k is not equal to I. So basically, when this term is not even in the row where the only non-zero element is, because k corresponds to the row, right? So if k is not in the ith row where the non-zero element is, then all the elements in the kth row would be 0. Hence, we can claim that then row ij km is equal to 0 for all m, because it wouldn't matter whatever column you are in, as long as you are in the column with, as long as you're not in the ith column, because all entries in that column, in that row, would automatically be 0. I said ith column, I meant the ith row. You get the idea, right? Because again in this example, let's say this is the row where we have that 1, right? But you're not even in this row. That row is entirely full of zeros, so you would always get a 0 as that product. So now we've automatically proven this for all those things where k is not equal to I. So our proof is much more simpler now, because we only need to now prove that this is also the case for k is equal to I. So let's take, so if k is equal to I, um, then we have row ij square kl, which is row ij square k can be changed to I, right? IL, which in turn can be rewritten in the sigma notation as m is equal to 1 to n row ij im times row ij ml. Makes sense, because we are essentially doing what we did up here. Just the k is now replaced with the I. Again, I need to make some space. I should practice writing a bit smaller, but it is what it is. Now, this element, the ij, for the only element in this, like again, I'll draw the visualization. Now we are in the ith row, right? And these are, say, the different columns. Say if this was the 1 and all others were 0, then only this column and this column can give us some hope of a non-zero product. All other columns already are 0, so they would automatically be give us a 0 product. So this was the ijth entry. So only the product which we obtain from the ijth entry from the jth column in the first matrix can possibly give us a non-zero sum. If it gives us, so now we are going to check what the other element would become. Here our m would now be j because we are in the jth column. So now again this would be row ij JL. Now we run into the same error because we are for this product to be non-zero, both of them have to be the element which is non-zero, right? And the non we are getting the non-zero element on this end, but on this end our element is a zero element because the non-zero element is in the ith row, but we are already in the jth row. The jth row will not have any non-zero element, so this product would automatically become zero. So essentially we've shown that this term, I'll go up a bit, row ij square would always be 0 even if k is not equal to I or k is equal to I, which upon going back here is what we needed to prove, because this term, I'll switch to the black pen now. Yeah, this term and this term, we've proved that they are 0, so ef is equal to fe is equal to I, and hence we've proven that row operations, the elementary matrices corresponding to row operations are invertible, and this also proves that the all the row operations are invertible, because now you can see that the changes done by E are nullified by changes done by F. And I had explained earlier what E was doing was adding C times row J, and what F did was remove C times row J. So in effect, they nullified each other. I hope you guys like this proof. And if you want more such proofs, then of course like, share, subscribe, and comment down below any other proof which you would like to see.